Hi, Lauren, you are on mute.
You're still muted, Laurent. Could you unmute? Can't hear you. What's going on? Is anyone else hearing us? Can someone give me a...
Whoops.
Oh, there we go.
Yeah, do you hear me now?
Yeah,
yes, yeah. Okay.
Yeah, so sorry about that. Yeah. Hello, everyone. Thanks, Vray, for the introduction and the invitation. Today, I'm gonna present you broadly my paper, Hands-on Bayesian Neural Networks, a tutorial for deep learning users. We should introduce the concept of Bayesian neural network, what they are meant to do, why they are useful, when you want to use them. Then I will present a general workflow to use those Bayesian neural networks, from defining the model, defining the learning strategy and which kind of learning algorithm you can use. Then, as Bayesian neural networks were more derived for shallow and small architectures, they are not so well scaled for the big models used in deep learning today. So I will present some approximation that you can use to get faster algorithm. Then once you get your Bayesian neural network, I will present you how to measure the performance and give you a short overview of the frameworks you can use to implement your Bayesian neural networks and all other stuff in Bayesian deep learning before concluding. So I assume most of you as PhD students in a deep learning group are already familiar with the concept of artificial neural networks. That's a great tool. They work as a universal function approximator. And yeah, everything is fine until it isn't. Like, what if I add a bit of adversarial noise and I can make a neural network goes crazy? Or what if I put a bit too much parameters and the network just overfit the data set, which lead to very good training error, but can just lead to crappy results everywhere else. And last but not least, one of the major problems with standard artificial neural network is they are not so good as accounting for uncertainty, which is related to the other problem I presented. And why is that? Yeah, that's because when you train an artificial neural network, you usually get only 1 point estimate, one possible parameterization. That might be the optimal parameterization to feed the data set. But what if a slightly less optimal parameterization is just better outside the training set? So that's why you might want to consider not just 1 point estimate of the parameters, but get a probability distribution over the parameters, which let the neural network quantify uncertainty. You can also put the probability distribution on the activation of the network. Both models exist in the literature. They can be shown to be somehow equivalent. How do you train such a network now? Well, there's that great tool called Bayesian, shown here, which works by inverting conditional probabilities. And why is it so great? Well, first, in Bayesian statistics, you have to interpret it like that. H is an hypothesis, and D is some data. So in the case of deep learning, D would be the training set, and H might be the parameterization of the neural network. And it's quite easy to define the conditional probability of the training set given a parameterization. And if one can also define a prior probability for the parameterization, then using Bayes' formula, it's possible to find directly the probability of the network parameterization given the training set. But yeah, you have to define that prior belief to get something useful. In deep learning, this is usually done by deriving the prior from regularization methods. Should show that later on. So now, how do we define a Bayesian neural network? Well, we said we have point estimate neural networks, and the stochastic neural networks, which do not account for just one parameterization, but the probability for any parameterization. And then we have the Bayesian methods, which are a subset of regularization. And now we define the maximum likelihood point estimate neural networks to be unregularized point estimate neural network, the maximum a posteriori point estimate neural networks, which are point estimate neural networks, but trained using Bayesian formalism, and the neural networks that we are interested in today, the Bayesian neural networks, which are stochastic neural networks trained using the Bayesian paradigm. Why should you use them? Well, for a multitude of reasons. Well, first, to measure the probability of an output, the prediction uncertainty. And even if there are other methods, Bayesian neural network have been shown to be better calibrated. They have the added benefit of limiting the risk of overfitting. I mean, if you consider all possible models, you consider all possible way of generalizing. And instead of having a big error, well, you would still have a big error in most cases, but instead of having just a big error and no clues about it, you get a big uncertainty in the data you are not able to fit properly. And yes, why would you matter to define a prior? It's complex, isn't it? Well, turns out that mathematically you can argue using the no-free-lunch theorem in learning that if you try to avoid defining a prior, you are still defining a prior. It's just implicit. And on top of that, the cherry on the cake, the Bayesian paradigm offer a great tool to analyze learning strategies, which would be useful even for point estimate neural networks. Okay, so Bayesian neural networks are great, but how do you work with them? So you start with different inputs. You need a stochastic model, which includes your prior and possibly a variational posterior, depending on how you will approximate the posterior later. You need a functional model, which is your neural network architecture. And you need some training data. You input all of these into an inference algorithm, which correspond to the training phase. And mostly you can distinguish two kinds of inference method, Markov chain Monte Carlo, which allows you to sample the exact posterior, but tends to be a bit more expensive, both in terms of memory requirements and computational power. and variational inference, where you approximate the posterior using the variational distribution you defined in your stochastic model. Okay, from the inference, you get the posterior, which is the probability of the network parameterization given the data set. And now, if you get a new input X, you can just marginalize given that posterior and the functional model to get the probability distribution of the output, knowing that input and the training set. And since this is a complete probability distribution, you might want to summarize it with the maximum a posteriori estimate for the output, but also a measure of uncertainty. So great. How do you define your stochastic model now? Well, there's that great things called probabilistic graphical models, which allows you to define, explain the relation among the different stochastic variables you consider in your model. And in Bayesian deep learning, we limit ourselves to directed relation, which means that one variable is dependent on the other, but the other is independent on the first variable. You define new variables using a full colored cycle for the observed variable, white cycle for the latent variable, unobserved one that you are trying to learn. You might indicate deterministic function using dashed cycles. You can indicate parameters using squares. And you can indicate that you replicate an experiment multiple times using a plate, which implies that the graph is duplicated across the batch dimension B, and that each realization is independent. Okay, so you put your variables in square and cycles, you draw arrows to explicit the relation amongst them, but then you should still define the probability distribution. Well, the PGM, probabilistic graphical model, will tell you exactly how you should do that. So first, you can compute the joint probability of all variables using the fact that the graph is undirected. You can just make the product of the probability of each variable, knowing its parents. And it means you just have to define those probabilities for each variable, knowing its parents. For a plate, you can use independence across the plate and just make the product of the probabilities. And then you can derive the posterior for the latent variables, knowing the observation by just integrating over the latent variables and dividing the full probability distribution by that integral. It's straightforward to see that this is equivalent to Bayes' theorem. Okay, so this is nice. Now, you might think, yeah, great, but what kind of probability distribution should I use? Well, first, in the case of Bayesian neural network, you might want to define the probability distribution for the parameterization. And I said this is linked very closely to regularization. Why is that? Well, let's just look at the loss that is usually used in training. And what you do most of the time is minimizing that loss. But one could also consider that the loss is equivalent to the log of a probability distribution, which is the probability of the output given the input and a parameterization. This is true up to a constant most of the time. And so minimizing the loss is equivalent to maximizing the likelihood. And now, what if you add just a regularization function that works on the parameterization, but not on the data? Well, in that case, if you switch to the probability formulation, you see that's equivalent to multiplying your likelihood by a prior, which is exactly what you do in to derive Bayes formula. So this is a generic tool that is usable most of the time to derive the exact probability distribution. You might also want to include more prior knowledge in your stochastic model. Usually saying like, for example, in image processing, I want prediction that are piecewise continuous, or in signal processing, I might want predictions that are sparse. And how you do that is usually add a consistency condition to your loss. Well, in the same way, you can use that consistency condition in your stochastic model, just derive a probability distribution of the parameterization of your network, knowing the input data, by just taking the exponential of this consistency condition, which can be useful in a lot of cases, like for example, semi-supervised learning. Great, so now you define your stochastic model, you define your functional model. I assume you are familiar how to do that. And now, how do you link both together? Well, let's see a series of practical examples, like a very basic, just fully supervised neural network that is a Bayesian neural network. So, feed forward, you get the input data that is observed, the output data that is observed, and the parameterization of the network that is a latent variable. You just have to define the probability of the latent variable, which you can do, for example, with a normal law. If you have an idea of a parameterization that is supposed to work, you can put a mean to that normal law, but most of the time you would just set the mean to 0. And the standard deviation to a reasonably large value, depending on the expected range of parameter in your network. And then you just assume that the network is able to approximate the outputs up to a certain standard deviation, and you do just a normal, setting the mean using the output of the neural network. Pretty straightforward. In the case of stochastic activation, it's a bit different. You see now that the parameterization is not a stochastic variable, but a parameter. And the latent variables are the intermediate layer in the network. You can define a series of normal law for each activation, where the mean is given by the previous layer. And in fact, it's possible to choose the standard deviation matrices such that both models are equivalent. So it's mostly which model you find more instinctive, more suited for your application, but both are perfectly valid. Okay, you can build on top of that. Like, assume, for example, you get some labels for your dataset, but you are not perfectly certain they are correct. Like, for example, you crowdsourced them. like, then no problem, you can extend your stochastic model. So now the true labels are unobserved, and what you observed is a derived variable that depends on the true label, but might be changed. And you can define noise using different models. Like, for example, if you're just receiving the labels from a noisy channel with uniform independent noise, you will just get random corruption. While if you get a case that is a bit more complex, like you are crowdsourcing labels for animal pictures, then rare animals like weasels are more likely to be mislabeled than cats and dogs, which everyone know. And in that case, you can make a model a bit more complex, or even put some dependency on the input variable. Another case is where you got only a small data set, or there is a behavior of your model that you want to enforce in your data set, like rotation invariance in image processing. Usually the way to do that is via data augmentation. Okay, so how do you account for data augmentation in a Bayesian neural network? Well, you could just extend your data set and do the supervised training as usual, but that wouldn't be perfectly correct from a stochastic point of view. So what you should make explicit instead is that from the observed variables, you derive some unobserved variables that represent your augmented data set, and you use that for training. So it means that if given a certain input and certain output, you can randomly assume that a different input is very likely to give an equivalent output, which also allows to account for the uncertainty correctly. There's more details in the paper if you are interested. Another example, in deep learning, you usually want to transfer some knowledge. Would it be for meta learning, like learning to learn? So you want to learn strategies that allows your model to converge more quickly, or get better results, better generalization. Or for transfer learning, you learned something on a given data set, and now you want to learn something on an equivalent data set, but you want to reuse that knowledge. How you do that? Well, no problem. You add a Xi variable that encode the general knowledge that account for the different tasks, and then you nest plates together, a method called hierarchical base. And you have the first level example here, but it's pretty straightforward to generalize at more level. Like if you get two tasks that are more closely related and one task that is distantly related, just add one new plate and one top level variables on top of that. Nice. Well, very nice. Okay, you know how to define your model, but now how do you train them? Well, there's those two inference methods. First, the Markov chain Monte Carlo. The general principle is to have a series of variables that you sample, and those variables, even if they might be correlated with one another, in the long term, they follow the underlying distribution. Okay, so this is good. This allows to sample the true posterior, but it means you have to store a lot of samples to be able to decorrelate them later and resample from that batch. Good example would be the Metropolis Hastings method, where you have a proposal distribution Q, which allow you to sample the next next value. Q can be almost anything. If you choose Q properly, you get some nice properties which lead to better and more efficient implementation of the algorithm, but this is the most generic form. And you see that you derive probability of acceptance for the new sample. And if you you get to accept it, then you can continue, else you need to resample over and over again, which can be pretty expensive computationally speaking. So instead, most of the time, what you want to do is use variational inference, where you try to approximate the posterior with a distribution Q that is much, much easier to sample than the true posterior. And what you do next is minimize the Kullback-Leibler divergence between Q and the true posterior. But since this imposes to know the posterior, what you want to do most of the time is maximize the evidence lower bound instead, which is in fact equivalent to minimize the ELBO, since both are equivalent up to a constant, which is the probability of the data set. Then you get a learning algorithm that can be made almost equivalent to the usual backpropagation algorithm. The main difference here is that it's a stochastic algorithm. You take a sample of the ELBO and then you perform backpropagation, and over a large number of samples, this should average out and converge to a maximized ELBO. Okay, great. But even that can be pretty expensive for a very large network. So what can you do to be even faster? Well, there's different methods. There's been a lot of research on a specific inference method, which can be split mostly first between variational and Monte Carlo methods. And the two approaches they are using, either droplet and other kind of noise layers, or the stochastic gradient descent dynamic, which can be reinterpreted in a Bayesian way. And there's other simplification methods. First, you can use only a few Bayesian layers at the end of the network. The other one are learned deterministic transformation, which allows to simplify things a lot. And you can also use Bayesian neural network teachers to try to compress the knowledge of the Bayesian neural network in a point estimate network. Why would you do that? Well, to avoid having to perform the marginalization at the end during the prediction step. Monte Carlo droplet, that's a method that is used quite a lot. The idea is to use dropout, which is a method that will randomly turns neurons in or out during training to force them to not co-evolve. But if you keep your droplet layers activated at evaluation time, you can see that method like some variational inference, where you fit random distribution using Bernoulli variables to define the weights. But since now dropout is used as a variational distribution, to be perfectly Bayesian, you still need to add another prior. But else, it's really straightforward. You can implement that in any deep learning toolbox. So that's why it's pretty popular. Another algorithm that is very popular is using the dynamic of stochastic gradient descent. The most well-known algorithm is SGLD, stochastic gradient length-driven dynamic, which the idea is to add just the proper amount of noise to make sure that instead of converging to a single point, stochastic gradient descent just bumps around in a way that is equivalent to a Markov chain Monte Carlo that samples the exact posterior. This is also quite easy to implement in traditional deep learning framework, but it has one major problem. It will give you samples that are more and more correlated. What you can do instead is use warm restarts. And there's two approach. Well, you can use warm restarts with SGLD to kill that self-correlation across samples. Or you can say, okay, well, I don't care about the exact shape of the posterior because, well, if I get points that are on the same mode, okay, they might lead to slightly different predictions, but they will tell me the same thing. To get a good idea of uncertainty, I should instead focus on the different modes of the posterior. And to do that, you can just restart a stochastic gradient descent, either with a greater learning rate and with a new random initial position. And like that, you should be able to converge to the different modes of the posterior. And you need to store less of them to get a much better estimate of the final uncertainty. Another thing you can do, as I said, you can limit the number of stochastic layers. Why? Well, because the idea of deep learning is that you learn a transformation that allows you to learn a linear transformation to fit your data. And you can just have the uncertainty on the final layers, 1, 2, maybe 3 of them. And the initial point estimate transform is just, can be seen just as a transform you are given. Well, you are learning it, but from a statistical point of view in your model, that's a deterministic function that is given. Like that, you can simplify the management of your Bayesian neural networks. Another things you can do is, well, you don't want to use Monte Carlo at evaluation time. So, okay, you do that a few times on a training set, and you get as labels both the maximum a posteriori estimate and some measure of uncertainty. And then you train a point estimate neural network to approximate a distribution, a variational distribution Q, to approach the posterior distribution you are seeing for the training set. And how do you match them? Well, like for variational inference, you want to reduce the distance between the two distributions, and you can do that with the Kullback-Leibler divergence. And you then get a point estimate network that gives you a certain prediction calibrated by the Bayesian neural network. Why don't train a point estimate neural network in the first place then? Well, the idea is to train with a data set that is much larger than the training set you used for the Bayesian neural network. Why? Because the Bayesian neural network gets uncertainty and needs the labels, while at the second step when the Bayesian neural network becomes a teacher. It gives the label, so you just need the inputs. And it means you can have a much, much larger data set and train the student networks with much more confidence that you are not going to overfit. Nice. So you get your Bayesian neural network, you trained it, and now you want to check how it behaves. Is it giving you good performances? Well, you can check if the maximum a posteriori estimates match your labels in some kind of test set, like for standard neural networks. But since Bayesian neural networks are stochastic neural networks, you also want to check that the probability distributions they are giving you are meaningful. How you do that? Well, one of the most popular way is to use calibration curves. The idea is to compare the empirical observed frequency against the predicted probability. If you give a lower probability than the observed probability, then you're underconfident, and this is bad. And if you give higher probability than the observed probability, then you are overconfident, and this is also bad. What you want to do is be as close as possible to a straight diagonal line in that squares, which is a perfect calibration. Okay, so nice. Now I told you how you should design, train, and assert the behavior of your Bayesian neural networks, but you might still be wondering how do you implement them? Well, there's two approaches. The first is to use a probabilistic programming language. So a probabilistic programming language is a framework to implement, manipulate, and use probabilistic graphical models on a computer. The benefits they have is they can work with very complex stochastic models easily, but most of them implement just basic mathematical primitives for everything else, which means that all the primitives for deep learning will have to be recreated from scratch. Some of the most popular PPRs are Stan, which is it's its own programming language, but it's got bridge to most popular scientific packages like Python, MATLAB, R, and so on and so forth. And PyMT3, which is a Python library. Okay, this is nice, but what if you get a framework for deep learning that is also a probabilistic programming languages? Well, in recent years, there has been some development in that direction since, well, there's a need to measure uncertainty in deep learning, and it appears that PPLs and deep learning frameworks are based on the same primitives like automatic differentiation and linear algebras. So there's been that Edwards PPL that was implemented on top of TensorFlow, and now the version 2 has been made into a proper subpackage of TensorFlow probability. And if you prefer to use PyTorch, then there's been that Pyro library that has been implemented on top of it. And Pyro also received a NumPy backend recently, if you're more on the CPU side of computation. Nice. So, in conclusion, Bayesian neural networks are great. Yeah, now they offer some advantages on their point estimate relatives. The main problem they have is they are more complex and expensive to compute. So you need some simplification strategies. But hopefully there exist some simplification strategies. You can use the Bayesian modeling framework to create, understand, and analyze a lot of different learning strategies. And even if in most research articles, you won't find so much practical applications for Bayesian neural networks, might be due to the fact that they are just seen as a tool to measure uncertainty, which, well, they prove they can do that, so no need to publish more paper about that. Yeah, well, this is, I don't agree completely. I mean, we showed that Bayesian modeling also allows you to create new learning strategies. And another main problem was mostly that implementing them was hard, but with the new addition to TensorFlow probability and the Pyro library built on top of PyTorch, that might change in the near future. Okay, so if you are interested, there's much more details in the paper that couldn't fit in a 1 hour presentation. So you can see the paper, the preprint of the paper published on Archive. And if you have any question, well, you can ask them now. And if you have any question later, you can also email me. I am more than happy to discuss about Bayesian neural networks with you.
Okay. So, so I'll hit up just some general questions. What are you doing now, Laurent?
What am I doing now?
Yeah, where has this taken you? So what's your current work?
I'm currently working on Bayesian neural network for stereo matching, and I'm trying to derive new learning strategies to use Bayesian modeling to improve results of semi-dense stereo matching, not just get an idea of uncertainty.
Okay. And one of my issues with the with this area is that there's really so much of it, and I'm encountering good work all the time that sort of we didn't really fit into that original review, and so it's sort of hard to know where to put the boundary, though certainly a general overview is a good thing to get started. Have you had any sort of retrospective thoughts about important areas? I think your slides kind of lay out the bits, you know, estimating uncertainty, getting the calibration, building networks in different ways. Is that it, do you think? Or do you think you've got perspectives you want to put in that could be good for understanding this general area? Perhaps that's a bit too general, but you know, I'm
Yeah.
just wondering what
Well,
would go into the paper next, maybe.
Well, there's a lot of things that we didn't cover in the paper. I think we skipped Bayesian unsupervised learning completely. I mean, you can see in the slides the examples of probabilistic graphical models that I showed. Most of them were supervised or semi-supervised. There's a large field of unsupervised methods in Bayesian statistics that we didn't cover in the paper. There's also lots of application of Bayesian methods in active learning, which we covered shortly in the paper, but I skipped in those slides. Well, for those who don't know, active learning is the process of getting a unlabeled data set or partially labeled data set and have the network ask which which example should be labeled next to get the stronger improvements during training, which Bayesian neural networks are good at because you just select the more uncertain example. And if you get a label there, that will reduce uncertainty a lot.
All right. Any other questions there? Are you on lockdown over there in Western Australia? You guys are meeting and sort of, you don't have any crowd restrictions? Or?
No. No.
I know one of my students is trying to get moved. She's a PhD student, trying to move back to WA, complete her PhD. She's been scared off by
yeah.
all our lockdowns. Okay, well, if that's the end of it, we'll thank you, Laurent, and that was a nice overview for me.
Yeah. Is there any other question beforehand? Yeah, I don't know. How do I check? How do I check? Is there anyone on the chat? I'm not.
Oh, I just checked the chat. Yeah. Yeah. All right. You look like you're in a room.
Yeah. I'm in uni right now.
All right.
I'm in uni right now.
Yeah. We did have a comment from Sachif, who's just about to get his PhD in probabilistic programming.
Yeah.
So of course he just saying it was good to see the small section there, which I think is important, that area, because of the really the role that programming language activity with PyTorch and that have had on. The only reason deep neural networks is successful is because of the automatic programming technology that's been put into it. So I think probabilistic programming, for me, has a big role to play in furthering any kind of Bayesian deep learning. So embedding some of the techniques for ensembling or putting, you know, Bayesian layers on parts of the network, that should be something we embed into the libraries.
Yeah.
So hopefully someone will take up that task. Okay, well, there we go. So thank you all. Teresa will have the recording in a bit, and we can send you along the MP4 when that's done. We'll give you access to it. You can also request it gets deleted if you want. But usually it sits in a repository here, and it's only accessible to